Hi, in this video, we are going to look at functional equations. This is the third class in the course. And today we are going to start a discussion on the topic of equations on natural numbers. So we are going to look at functional equations which are on the set of natural numbers. So n is to n usually, right? So what are the important properties of this set of natural numbers that we will be using in our equations? So first of all, the set of natural numbers obviously begins from 1, 2, 3 and goes on forever. And it follows the following properties: the additive property, the multiplicative property, and also ordering. So what do I mean by these things? So first of all, the additive property means that if you take any two natural numbers, any numbers from this set, when you add them, the result is also a natural number. So addition is natural number set is closed under addition. Similarly, it is closed under multiplication because when you take two natural numbers and multiply them, the result is still a natural number. Then we have the ordering property that any two natural numbers can always be grouped and can always be ordered, or you can always say either A is greater than B or A is less than B or A is equal to B. So this ordering is clear at all times, right? So we will see how these properties will be used in the context of problem solving on functional equations. Later, we'll also introduce the ideas of induction. Induction is a powerful technique to prove functional equation problems, and also the well ordering principle. So I will discuss that as we get into the class. So the well ordering principle basically says that any non-empty subset of natural numbers has a least element. And we'll use that property as well while we prove things, right? So let's begin with the first problem. And this says, find all functions f goes from n to n such that property A is f of 2 is equal to 2. Property B is f of mn is equal to f of m times f of n when m and n belong to natural numbers. And property C is f of m is greater than f of n when m is greater than n. So basically, if you think about this property is saying that the function is multiplicative, right? The output of mn is the same as the product of the outputs of f of m and f of n. And this property says that the function is an increasing function. So we are going to look at a multiplicative increasing function over natural numbers n to n such that all of these conditions are true and f of 2 is equal to 2, right? So using this result, using B, if you put m is equal to n is equal to 1 there, you will get f of 1 is equal to f of 1 whole square, which means that f of 1 can be 0 or 1. And that implies that f of 1 must be 1. It cannot be 0. 0 is rejected. The reason being that the domain and range are natural numbers. So the range is natural numbers and 0 is not a natural number. So f of 1 must be 1. So that is the first thing that we know. Similarly, you can find that f of 2 into 2 is equal to f of 2 times f of 2. So basically you get f of 4 is equal to f of 2 squared, but f of 2 is 2. So f of 4 is 4, right? Once you know f of 4 is 4 and f of 2 is 2, because of the third property C, we can say that since it's an increasing function, f of 2 will be less than f of 3 will be less than f of 4, and f of 2 is 2 and f of 3 is unknown, and this is less than 4. The only natural number between 2 and 4 is 3. So this implies that f of 3 is 3, right? Similarly, you can find f of 6 is equal to f of 2 times f of 3, and that becomes 2 into 3 is equal to 6. And now that we know f of 6 is 6, by the same logic, you can say that f of 4 is less than f of 5 is less than f of 6 because of property C. And f of 4 was how much? F of 4 was 4, f of 6 was 6. So that guarantees that f of 5 must be 5. because 5 is the only natural number that lies between 4 and 6, right? So basically using the property C, we have basically figured out f of 1 is 1, f of 2 is 2 was given. We figured out f of 3 is 3, f of 4 is equal to 4 we got from property B, and f of 6 is 6, and using these two and property C, we figured out f of 5 must be 5, right? So our conjecture is that f of n will be n, right? It looks like f of n should be n. So we'll use now strong induction and we'll say, suppose f of 1 is equal to 1, f of 2 is equal to 2, and we have proved that up to 2k, f of 2k is equal to 2k. We are using strong form induction. So all the values up to 2k we have assumed are equal to 2k. And here k is some natural number. Some natural number. Then let's calculate f of 2k plus 2, which is going to be equal to 2 times k plus 1. So because of the multiplicative nature, this is f of 2 times f of k plus 1. And that is basically 2 f of k plus 1, right? Great. Now notice that f of k plus 1 was in this set of numbers, because here the set of values that we know are f of 1 to f of 2k. So f of k plus 1 is already inside this set. That is k plus 1. So therefore we get 2 times k plus 1 here. So which is 2k plus 2. So we have proved that f of 2k plus 2 is 2k plus 2. But that doesn't do our induction for us. For the induction step, I need to prove the next one, which is f of 2k plus 1. We have to show that f of 2k plus 1 follows the same pattern and is equal to 2k plus 1. What we have right now is f of 2k plus 2 is 2k plus 2. So now we will use the same logic that we did for f of 3 and f of 5. We will say that f of 2k should be less than f of 2k plus 1 should be less than f of 2k plus 2. And we already know this is 2k by the induction hypothesis here. And we know just now that this is 2k plus 2. So which natural number lies between 2k and 2k plus 2? Obviously, the only natural number there is 2k plus 1. So therefore, f of 2k plus 1 must be equal to 2k plus 1. And that is our induction step. That tells us that from the strong induction assumption, we are able to go to the next higher step. We are able to get f of 2k plus 1. And therefore, our induction is complete. And the only function that satisfies this is f of n is equal to n. That was our hypothesis, that f of n is equal to n is this function, right? So that finishes off the first problem. And notice how we used induction in the problem. Now, a slightly different problem, which is a variant of the first problem, but here we will relax the second condition. So the question says, find f of n to n, which satisfies first of all, f of 2 is equal to 2. Then f of mn is equal to f of m times f of n only when GCD of m and n is equal to 1, right? And then part 3 is saying f of m is less than f of n if m is less than n. So notice that the first and the third conditions are the same as the previous problem, but the second condition is a weaker condition. Why is a weaker condition? Because earlier we said that the function was multiplicative for all m and n. Now we are saying that it is multiplicative only when the m and n are relatively prime to each other, right? So following the previous problem, we can easily get f of 1 is equal to 1. You put m and n equal to 1, you will get f of 1 is equal to 1. But now we can't conclude, we can't say that f of 4 is equal to 4. Because 2 and 2, if you try to put 2 and 2 doesn't follow the multiplicative property, because GCD of 2 and 2 is not 1, it is 2, right? So basically we don't know f of 4 is 4 or not, right? Now think about it. If we knew that f of 3 is 3, We know f of 1 is 1, f of 2 is 2. If we knew that f of 3 is 3, then we could have said, f of 6 is equal to f of 2 into f of 3, because when you write 6 as 2 into 3, 2 and 3 are relatively prime to each other. So we can use this property. Then we would have gotten 2 times 3 is equal to 6. And once you get f of 6 as 6, you will be now able to say f of 3 is less than f of 4 is less than f of 5 is less than f of 6 because of property C, which is an increasing function. And f of 3 is 3, we have assumed that. And f of 6 we have just now gotten as 6. If 3 is less than f of 4 and f of 5 and less than 6, there are only two natural numbers between 3 and 6, which is 4 and 5. So therefore, f of 4 must be 4 and f of 5 must be 5, right? So basically, if we can show that f of 3 is 3, then we will be able to prove that f of 4 is 4, f of 5 is 5, f of 6 is 6, right? And after that, I will first show you the induction. So after that, we can finish the induction also. So what we will say is, let's say GCD of two numbers k and k minus 1 is equal to 1. This is a fact for any k greater than equal to 2. This is true from number theory. Any two consecutive numbers are always relatively prime as long as the numbers are bigger than 2, right? So suppose we assume that f of k is equal to k for all k less than equal to n. So again, we are doing strong induction. We already have right now, we have already assumed f of 3 is 3. And now we have this much information. F of 1 is 1, f of 2 is 2, f of 3 is 3, f of 4 and f of 5 are 4 and 5, and f of 6 is 6. So our conjecture right now is that f of n is n, and we are trying to prove that by induction, strong induction. So we have assumed that f of k is k for all k less than equal to n. Now, if I try f of n minus 1 times n, because these two are co-prime, I can use property 2. So this will be equal to f of n minus 1 into f of n. So that will be equal to n minus 1 into n, right? Basically, we have assumed strong induction. So all of f of 1, f of 2 till f of n is n. That we have already assumed in the first step, right? So this is coming as this. F of n minus 1 into n is equal to n minus 1 into n. Now we can say that by the property C, and similar to what we have done earlier, n is equal to f of n, but that is less than f of n plus 1, that is less than f of n plus 2, that is less than so on. We can write less than f of n square minus n minus 1 is less than f of n square minus n. And that is equal to, just now we have found out f of n square minus n is equal to n square minus n, right? So this sequence of inequalities where we are starting from n and going up to n square minus n, in the same way as we did for f of 3 and f of 6, and from there we got f of 4 and 5, from here we guarantee that the only possibilities for this are n plus 1, n plus 2, and for this it will be n minus 1 into n minus 1, right? Which is n square minus n minus 1, right? So notice that f of n plus 1 lies inside this sequence. So f of n plus 1 comes out to be n plus 1 from here, right? F of n plus 1 we get because it is in this sequence of inequalities. The value of f of n plus 1 comes out as n plus 1. And therefore, if you assume everything up to f of n is n, then you can show by a strong induction that f of n plus 1 is n plus 1. And basically the proof is done, and we have shown that f of n is equal to n satisfies this functional equation. So all of it, however, rests on the fact that can we prove that f of 3 is 3? Because unless we get f of 3 is 3, we cannot do anything about f of 4, f of 5, and f of 6, and so on. So now our job is basically proving that f of 3 is 3. So let's see how we can do that. So first of all, if you think about what is f of 15, what is that? This is 3 into 5, and 3 and 5 are co-prime, relatively prime to each other. So that is equal to f of 3 into f of 5 by the multiplicative property. And obviously, f of 15 is less than f of 18. And f of 18 is equal to f of 2 times f of 9, because 2 and 9 are co-prime to each other. So this will be 2 times f of 9, right? So what we get is f of 15 is less than 2 times f of 9. And what is f of 15? It is f of 3 times f of 5. So we have gotten this inequality. F of 3 times f of 5 is less than 2 times f of 9. So keep that in mind. Now, another inequality that we can create is f of 9 is less than f of 10 because it's an increasing function. But f of 10 is equal to f of 2 into 5. By multiplicative rule for co-prime numbers 2 and 5, we can write it as f of 2 times f of 5. And that is basically 2 f of 5, right? So we are getting f of 9 is less than 2 times f of 5, right? Now, combining this inequality with this inequality, we get f of 3, f of 5 is less than 2 f of 9, and 2 f of 9 will be less than 4 f of 5. So we are getting f of 3 times f of 5 is less than 4 times f of 5. Since we are on the set of natural numbers, f of 5 and all is all positive, we can cancel it off. And we are getting f of 3 is less than 4. Now we already know that f of 2 is equal to 2, and we know that f of 3 is greater than f of 2 because of increasing function. And now we have gotten f of 3 is less than 4. Therefore, f of 3 must be equal to 3. And as soon as you get f of 3 value, we already showed that we can get f of 4, f of 5, f of 6, and eventually prove the induction as well, right? So that basically solves this problem. And even though the condition B was relaxed from the first problem, we were still able to complete the question, right? However, the argument that we had to use was slightly different. Okay, let's go to the third problem. This says, this is another variant of the previous problems. In this case, we are going to change the value of f of 2 and see whether it impacts our solution or not. So the question says, show that there does not exist a function f goes from n to n such that first condition is f of 2 is equal to 3. Second condition is multiplicative condition as we saw earlier. For all m and n belong to natural numbers. And third condition is the increasing condition. It's an increasing function when m is less than n. Right. So we have to prove that there does not exist a function like this for which f of 2 value is 3 and it satisfies the multiplicative and increasing nature, right? So we'll do a proof by contradiction, and we will assume that such a function does in fact exist, right? So if such a function exists, then f of 2 is equal to 3 and it satisfies the multiplicative condition and the increasing function, right? So let's assume f of 3 is equal to L. We don't know the value of f of 3. We are going to assume it as L. Now, if you think about it, what is 3 power 3? 3 power 3 is going to be f of 2 whole to the power 3. That is equal to f of 2 power 3 because of this multiplicative condition. But 2 power 3 is 8 and 2 power 3 is less than 3 powers 2. Because we know f of 8 is less than f of 9 by the C condition. Therefore, we can say this, and this is equal to what? This is equal to f of 3 square by multiplicative condition, which is L square. So we are getting a simple condition that 3 cube is less than L square, which implies that L is greater than 5, because this is 27 is less than L square. We are getting L is greater than 5. Now let's go to the next screen, and we are saying similarly L cube is equal to f of 3 whole cube, which is the same thing as f of 3 cube, which is f of 27, and that is clearly less than f of 32, which is equal to f of 2 power 5, which is equal to f of 2 whole to the power 5, right? And f of 2 we said in the problem was 3, so 3 power 5, right? So we are getting L cube is less than 3 power 5, right? So if you think about it, L cube is coming less than 243, correct? 3 power 5 is 243. So clearly that implies that L cube is less than 343, or it implies L is less than 7. So earlier we have gotten a condition that L is greater than 5. Now we are getting L is less than 7. So that automatically implies L must be 6, because it's a function on natural numbers, and the only natural number between them is 6. So we are getting f of 3 is 6, right? Okay. Now using this value, we will come to a contradiction. So we can try 3 power 8. 3 power 8 is 6561. And that is clearly less than 8192, which is 2 power 13. And what I'm going to say, we know these values, so we should have f of 3 power 8 is less than f of 2 power 13, right? So f of 3 power 8 will be what? Think about it. It will be 6 power 8 is less than f of 2 power 13. F of 2 was 3, so 3 power 13. So now if you look at it, 6 power 8 is less than 3 power 13 we are getting. But that is impossible actually, because 6 power, this is 2 power 8, 3 power 8 is less than 3 power 13. We are getting 2 power 8 is less than 3 power 5. And 2 power 8 is 256 and 3 power 5 is 243. So we are getting an obvious contradiction. We are getting 256 is less than 343. So this is a contradiction, which means that our assumption that such a function exists is untrue. When we use that assumption, we proved that f of 3 is 6, and we now are seeing a contradiction when f of 3 is 6, right? So such a function does not exist, and we have finished our proof basically, right? Let's look at another problem where we will relax condition C now, okay? So it's a variant of the same first problem. Now we are going to say something else. Show that there are infinitely many functions f from n to n such that, first of all, we are going to say f of 2 is 2, and b, f of mn is equal to f of m times f of n for all mn belonging to natural numbers. Notice that there is no C condition here. We have totally relaxed the C condition, right? So here we will use another fundamental property of the set of natural numbers, that every natural number has a unique prime factorization. And let's see how we are going to use that. So because we have this multiplicative property, anytime I want to find f of some number n, it will be enough if I know, because n can be written as p1 power alpha 1, p2 power alpha 2, and so on. It will be enough for me if I can figure out what is f of p1, f of p2, and so on. If I know the values of the function at all the prime numbers, then that is enough for me to find any f of n, right? So understand this fact. We already know that f of 2 is 2. We can use the previous methods to prove that f of 1 is 1 if you put m and n both as 1. So we know f of 1 is 1, f of 2 is 2. But think about it. If you want to know any other values, all you need to know is the values of the function at the prime number inputs, right? If you know all the values of the function at each of the prime numbers, then you can construct the function, right? So the first prime number P1 is 2, the second prime number P2 is 3, third prime number is 5, and so on. You have an infinite sequence of primes. So let's write that sequence here. 3 is equal to P2 less than P3 less than P4 less than P5. And this is the sequence of prime numbers, right? We are starting with the second prime number 3. This prime number is basically 5. This is 7. This prime number is 11 and so on, right? So this is a sequence of prime numbers. What I want to figure out is, can we get a function value for each of these prime numbers? Ultimately, I want to show that there are infinitely many such functions, right? So I will do it on the next screen. So this is my sequence of primes. P2 is less than P3 is less than P4 and so on. And this is 3, this is 5, this is 7. And now I will define for every k greater than equal to 1, the function f of k. The function f of k, okay? Now this f of k is basically defining a class of functions. Why? What do I mean by a class of functions? When k is 1, I am defining function 1. When k is 1. When k is 2, this is function 2. And basically, it's an infinite series of functions, right? There are so many functions that I can define for different values of k. And what is the way in which I am defining these functions? I am going to say f of k of p of j is always equal to p of j plus k. You can define it in other ways also, but this is one particular way of defining it for all j greater than equal to 2. What does this statement mean? So let's try to analyze one particular function f of 1. So f of 1 of p of j is p of j plus 1. So what this means is that f of 1 of prime number 2, prime 2, should be value of that should be prime 3. Similarly, f of 1 prime 3 should be prime 4. F of 1 prime 5 should be prime 6, right? So what is f of 1? What is the second prime number? 3. F of 1 of 3 is third prime number, which is 5. F of 1 of 5, which is the third prime number, is the fourth prime number, which is 7. F of 1 of prime 4, which is basically fourth prime number, is what? The fourth prime number is 7. So we can say from here that f of 1 of 7 will be the next prime number, which is 11. So basically, we are getting a set of values of f of 1 function at each of the prime numbers, right? How are we defining it? We are saying at any prime number starting from 3, the value of the function of f of 1 is the next prime number. And since the set of prime numbers is infinite, you can always find the values of the function at each of the prime numbers by finding the next prime number to it, right? From here, you will be able to construct any value for f of 1. F of 1 of 15, for example, will be f of 1 of 3 times f of 1 of 5. And notice that f of 1 of 3 was 5 and f of 1 of 5 was 7. So this is 5 into 7 is equal to 35. Similarly, f of 1 of 16 here would be 2 into 2 into 2 into 2, 4 times. So this is f of 1, 2 power 4. Because on the multiplicative property, it will be f of 1, 2 whole power 4. And f of 2 was 2. So therefore, this is 2 power 4 or 16. So notice that f of 1 of 16 is coming out to be 16. F of 1 of 15 is coming out to be 35. And clearly, this is not an increasing function. But definitely f of 1 is a valid function. Because we know the values of f of 1 at all the prime numbers, we can actually find the value of f of 1 for every natural number, right? Now, why is this a valid proof for our question? Because this definition also tells you how to define f of 2, a second function, f of 3, a third function, and so on. Because this definition can be extended for any j and k, right? So we can say f of 10 of pj is equal to p of j plus 10, right? So the 10th function will be such that all the prime numbers take the values which are another prime number but 10 spaces to the right, right? And it is still guaranteed to give you a function. The only difference is that it will be a different type of function. The set of primes is infinite, so you can guarantee that all prime numbers will get some value, right? We are using also here the fact that the set of prime numbers is infinite, right? And we have defined a class of functions which will always satisfy the conditions of the problem. This ensures that the multiplicative property will work and you can find out the values of the function at any other composite number as well, right? So that finishes off our problem here. The next question that we'll discuss is of a slightly different kind, where we'll introduce for the first time the principle which is known as the well-ordering principle, right? So I will just write down what is well-ordering principle. What this says is that any non-empty subset of natural numbers has a least element. Okay. So why is this going to be useful for us? So let's think about it. So if S is a subset of N and S is not equal to 5, then there exists a unique M that belongs to the set S such that M is less than equal to N for all N belonging to the set. Basically, M is smaller than any other element of that set. It seems like a very obvious statement, but we'll be using it extensively in problems. This is actually another way to frame the induction argument. So let's look at one example where we will apply this property. So this is question number 5. And this question says, if f of n to n such that f of n plus 1 is always greater than f of n for all natural numbers n. We have to prove that f of n is equal to n for all n belongs to natural numbers, right? This is a problem from IMO 1977. So an old IMO problem. So we start off by using the well-ordering principle, and we say let D be the least element in the range of the function, in the range of f. We are guaranteed that the range will have a least element by the well-ordering principle. So D is basically equal to minimum of f of n such that n belongs to natural numbers, right? Such an element definitely exists and such an element is unique. That is the well-ordering principle. Now we can say let m belong to natural numbers be such that D is equal to f of m, right? D is equal to f of m. So this D, which was the least element in the range, I am trying to say m is the number which is the input, which gives D as the output, right? The input which gives D as the output is my m, right? Now, if m is bigger than 1, right, then we can say that d is equal to f of m will be bigger than, by applying this condition, I am saying m is equal to n plus 1. Therefore, m is equal to n plus 1. So what is n? N is equal to m minus 1. So by applying this condition, I'm getting greater than f of m minus 1, right? So basically what we are getting is that f of m is bigger than this. But according to our definition, f of m should have been the least element, right? Now we get a different input, or a different out input f of m minus 1, such that the output of this f of m minus 1 is smaller than d. But d was supposed to be a minimum element, right? So this should not be allowed. This should never happen. Since d was supposed to be a minimum element, this can never happen. Therefore, this is a contradiction. We have used the condition given in the functional equation earlier in the problem itself, and we are using well-ordering principle to show that dm cannot be bigger than 1, right? So if m cannot be bigger than 1, the only option is m to be equal to 1, right? So therefore, what we get is f has a unique minimum. F has a unique minimum at 1, right? Now let's see how this will be useful for us. Now think of the set, consider the set of outputs f of n such that n is greater than or equal to 2. So this is the set of outputs starting from 2. So f of 2, f of 3, and so on, right? Similar to the previous argument, we can prove that this set also has a minimum element, has a least element, and by the same argument as before, we can say that the least value of this set is f of 2, right? The reason the least value is f of 2 is the same as earlier we saw that the least value of the overall set was f of 1, right? So we also know that f of 1 is less than f of 2, right? We also know f of 1 is less than f of 2 because f of 1 was the least element of the entire set. F of 2 is the least element of this range only, which is a reduced range, right? It's not the full range. So if we have this, we can basically say from here that we can repeat the argument multiple times and say that f of 1 is less than f of 2 is less than f of 3 and so on, right? F of n, like you keep repeating the argument for different values of n starting from 1, n starting from 2, n starting from 3, and so on. So I'm not going to write the same argument again. I'm just saying that repeating the argument, we come to this conclusion here. So now from here, we can say that obviously f of n, 1 is the least element. So f of 1 will be greater than or equal to 1. The output of f of 1 has to start off from 1 or more than 1, right? Now, this bound along with this condition tells us, since f of 1 is greater than or equal to 1, we now know that f of 2, which was greater than f of 1, should be greater than or equal to 1. So we know from here that f of 2 is greater than something greater than or equal to 1. So it implies f of 2 is greater than or equal to 2, right? So from here and here, we can combine and say f of k should be greater than or equal to k, right? For all naturals k, right? Now, what we have to ultimately show is that it is equal to k. I want to prove that it cannot be greater than k. So let's see how we do that. We'll do by contradiction. We'll say suppose that f of k is greater than k. If f of k is greater than k for some k, right? Therefore, then f of k, if it is greater than k, it should be greater than or equal to k plus 1 because the next higher output is k plus 1. Now, using the initial condition, which was f of n plus 1 is greater than f of n, we can say now that if I put f of k on both sides of this, we'll get this condition. We are getting f of k is greater than or equal to f of k plus 1, right? So now we are getting the opposite of this, right? We are getting f of k plus 1 is less than or equal to, right? This basically contradicts the problem statement itself. F of k is greater than or equal to f of k plus 1 is a contradiction of f of k plus 1 is bigger than f of n, right? So since this is a contradiction, then our assumption is wrong, and this assumption is wrong, basically. F of k is not greater than k, right? But earlier we had established that f of k is greater than or equal to k, right? So with this contradiction, we can now claim that f of k must be equal to k for all natural numbers, right? So basically what we are doing is we are using well ordering to first of all say that f of 1 is the minimum element of the entire set. Similarly, for smaller subsets of the range, we can prove that f of 2 is the minimum element for the range starting from n is equal to 2 onwards. And we get the condition that f of 1 is less than f of 2 is less than f of 3 and so on. But we also know f of 1 is greater than or equal to 1. So that means that f of 2 should be greater than or equal to 2. F of 3 should be greater than or equal to 3 and so on. Basically, we end up with the condition that f of k is greater than or equal to k, right? And then we have done a contradiction here that greater than k will violate the initial inequality. Therefore, it cannot be greater than k and it must be equal to k. So that is a nice problem where we exploited the well ordering principle. Let's look at one final problem for this session. This question says, find all functions f goes from n to n such that f of m plus f of n is equal to m plus n is equal to m plus n for all m n belong to natural numbers. Okay, no other condition is given. We will try and prove that f of n is equal to n satisfies this functional equation. It is obvious that f of n is equal to n will work. You can put n is equal to m here and you will get what? Or you can put this, you will get m plus n here and then m plus n is equal to m plus n. So we have a solution f of n is equal to n. We just have to prove that there are no other solutions, right? So first of all, let's see from here what we can figure out about the nature of the function. So if I put f of m is equal to f of n, if f of m is equal to f of n, then we can say that f of m plus f of n will be the same as f of n plus f of n, right? And if I apply f to both sides of this equation, what I'm getting is f of n plus f of n. And now using the relationship given here, what I can say is that this thing will be m plus n and this thing would be n plus n. So I'm getting n gets cancelled from here, m is equal to n. So what I have shown is that if you start with the condition f of m is equal to f of n, from there we are able to imply that m must be equal to n. This is the type of function that we discussed earlier, and this is called a one-to-one function. One-to-one or injective function. This was discussed in the previous class. So right now we know that our required function has to be 1-1 or injective, right? Now let's go to the next screen and try to rework with this given identity. We have this situation. So I want to create a similar identity here. What I will do is I will replace m with m plus k, where k is a natural number, and I will do n minus k, right? And I am getting m plus k plus n minus k here. As long as k is less than n and k is belonging to the natural numbers, this condition is valid. I have replaced m with m plus k and I have replaced n with n minus k, right? So notice that the right hand side here, the k part gets cancelled and you're getting m plus n here. So that can be replaced with f of m plus f of n, right? So what we are ending up with is a nice condition. F of m plus k plus f of n minus k is the same as f of m plus f of n, right? So this condition we will be using in our solution, right? Okay, so this condition is true. Now what we will do is we'll try to take some values. So suppose f of 1 is equal to b, and let's assume that b is bigger than 1, right? Let's assume b is bigger than 1. So therefore, b must be greater than equal to 2 then. So what we are getting is f of 2b will be equal to f of b plus b will be equal to f of 1 plus f of 1, because we have assumed f of 1 is b, will be equal to 1 plus 1. So we are getting therefore f of 2b is equal to 2 from here, right? And similarly, we can say f of b plus 2 will be equal to f of b. Instead of b, I can write it as f of 1. And instead of 2, now that we know that f of 2b is equal to 2, I can write instead of 2, f of 2b, right? And that will be equal to 1 plus 2b using the problems condition. So what I'm getting is f of b plus 2 is equal to 1 plus 2b, right? Great. Now here, if b is equal to 2, we had started by saying b could be greater than equal to 2, right? If b is equal to 2, we are getting a contradiction because we are getting f of 4 is equal to 2 using this condition, and we are getting f of 4 is equal to 5 using this condition. So that is a clear contradiction. So therefore b cannot be equal to 2. So now b therefore must be greater than 2. The only other case if b cannot be equal to 2 is b greater than 2. So now what we can say is f of 2b plus 1, f of 2b plus f of 1, we will use the condition that we have derived earlier. So what was that condition? If you remember, we had written f of m plus k plus f of m n minus k is equal to f of m plus f of n. Because the function was an injective function, we had gotten f of m plus k plus f of n minus k is equal to f of m plus f of n, right? So this condition was true earlier, we had proved, and now I'm going to use that here. So when I do f of 2b plus f of 1, I can rewrite it as f of 2b minus b minus 2 plus f of 1 plus b minus 2, right? I'm just applying this condition right now here, okay? So the reason I'm choosing 2b and 1 is because if you do b minus 2 subtraction and b minus 2 addition here, this becomes what? F of 2b minus b plus 2. So it is f of b plus 2, and this becomes b minus 1, right? F of b minus 1. So now I have gotten a result that f of 2b plus f of 1 is equal to f of b plus 2 plus f of 1 b minus 1, right? And we already got that f of 2b was 2. We already got f of b plus 2 was 1 plus 2b. And we had written that f of 1 was b, right? So we are getting 2 plus b is equal to 1 plus 2b plus f of b minus 1. And from here we are getting f of b minus 1 is equal to 1 minus b. But we already know that b is greater than 2. So we are getting f of b minus 1 is negative, which is not possible because our function was over natural numbers. So this is a contradiction, which means we had assumed b greater than 1. That assumption is wrong, right? While doing the question, we had assumed b greater than 1. So now we get that that assumption is being contradicted. And therefore, what we have is b is equal to 1 now, right? So f of 1 value is now equal to 1 for us. And the other values are still valid, like f of 2b for us is simply 2. So we get f of 2 is equal to 2 now, right? Correct. Now we can prove the thing by induction. We have f of 1 is 1. We have f of 2 is 2. And we will say, suppose for strong induction, we assume that f of k is equal to k for all k less than equal to n, right? Then using the equation f of n plus f of 1 is going to be equal to n plus 1. Using the initial condition of the problem, we are going to now write it as f of n was equal to n by strong induction. So this is n plus f of 1 was 1 is equal to n plus 1. So we are immediately getting the next step. If all the f of 1, f of 2, f of n is n, then we are getting f of n plus 1 is also n plus 1. So the induction step is done, and therefore we have the proof that f of x must be x or f of n must be n. That is the function that satisfies this functional equation. So here again, we use the fact that it was a 1-1 function. We simplified the 1-1 condition. If you remember, we got something like this. We got f of m plus k plus f of n minus k is equal to m plus k plus n minus k. We got this as m plus n. And then what I had not mentioned it earlier, what we could have written it as f of m plus f of n, right? From the given problem statement. And now notice that because this is equal to this, it is an into function, it is a 1-1 function. Therefore, we are able to say that f of m plus k plus n minus k must be f of m plus f of n. Because of the 1-1 nature of the function, we can remove the f from here and say that the inputs must also be equal if the outputs are equal. And this is the result that we used at the end when we said, assume f of 1 is b, find out f. We did a contradiction. We said, let's say b is greater than 1. And we showed that it is impossible. If b is greater than 1, you will get basically b should be greater than equal to 2. And you will get f of 2b is equal to f of b plus b. And what was that? F of 1 plus f of 1. And that was f of, that was 1 plus 1. That was 2. So f of 2b was coming as 2. F of b plus 2 was coming as 1 plus 2b. And we wrote the equation for f of 2b plus f of 1. And we wrote it as 2b minus b minus 2 plus f of 1 plus b minus 2. Here we are using this condition. F of 2b plus f of 1 is 2b minus this and 1 plus this. And after that, you saw all the steps. The contradiction was done where b is greater than 1 is proved wrong. So b must be 1. And once b is 1, you got f of 2 as 2. And after that, the induction is super obvious. So this is just the beginning of our discussion of equations involving functions on natural numbers. We will do another couple of classes at least on more problems, and then we will move on to other types of functional equations. The next type of functional equation that we look at is equations on real numbers, right? So stay tuned for more videos. I'll be making more content on this particular topic and problem series soon. And if you like the video, please subscribe to the channel, turn on your notifications, and share it with your friends. All your support will be extremely crucial for me to help reach more students. That's it for this video. I'll see you next time.